All right. Hello, everyone, and welcome to today's webinar on passive house design for structural engineers. My name is Bassem Al-Moody, the president of CMAS, and I wanted to welcome everyone to today's webinar. Before we begin, I just wanted to highlight a couple of upcoming events that we have with our organization. On August 11th, which is 2 weeks from today, same time, we have a T.R. Higgins lecture that will go into base plate connections. Their invite for that should be coming soon to your inbox, and so be on the lookout for that. We also have an upcoming webinar series, in-person series on steel coming up in September that we'll be sending out more info on soon. Now, before I introduce our sponsor for today, I wanted to remind everyone, if you have a question for our panelists today, feel free to use the Q&A chat box at the bottom of your screen below. If you run into any technical issues, feel free to message me directly and we'll try our best to help you out on our side. And so with that, I'd like to introduce first Passivhaus, Massachusetts. We have on the call today Hank Keating, who is the president of Passivhaus, Massachusetts, and Aaron Gunderson, who is their executive director. So I'll first hand it off to Aaron first.
Hello, everybody. Great to be here. I'm Aaron Gunderson with Passivhaus, Massachusetts. Those who are unfamiliar with us, we're a nonprofit organization that works here in the state and region to promote passive house buildings and high performance buildings. So we do a lot of trainings and education events and workshops. And we also do advocacy and outreach around passive house initiatives and financing and policies. Our main website, phmass.org, is on the bottom of your screen. You can find a lot of our events there, as well as a recorded library of all of our past trainings. So if you're curious about things that we've been up to or want to kind of get more in-depth information on passive house, please go there to the video library. My email is here as well, so you can reach out. In addition to Passivhaus, Massachusetts, I want to acknowledge Mass Save, who we've been working with for the last, well, about 4 years now to provide Passivhaus training programs. They've incentivized training for architects and others who take Passivhaus certification courses and do lunch and learns and workshops like this one. In addition to that, they sponsor incentives for Passivhaus buildings. I'm going to go on one more slide here. You can see these incentives have been out for now about 3 years, and they incentivize any multifamily project of 5 units or more to go passive house. As you can see, it's about $3,000 a unit. So fantastic incentive. In addition to that, they cover feasibility costs, feasibility study costs, and energy modeling costs, which go a long way to helping to offset some of those additional costs for teams. I would say that for most projects, even in the very early stage, if you're not sure if you're going passive house yet or not, take them up on the feasibility study. They will cover that, whether or not you go through with passive house certification. So it's a great way to sort of dip your feet into it and see how it goes. And hopefully it works out for your project and you can get the full incentives. But this is a great program. We currently have over 8,500 units registered into this throughout the state, which are incredible numbers. It's growing all the time. So it's been a huge success. It's been extended for another 3 years, so take advantage of it. Just this year, Mass Save rolled out incentives for 1 to 4 units. So remember, those were 5+ units. This is now 1 to 4 unit residential housing. And these incentives are based on going all electric. So rather than requiring passive house, they're requiring various steps to electrify the house. So you can kind of see they have 2 different sets of savings there, level 1 and level 2. I'm not going to go into all of these. It's just good to know they're available. You can find all of them at masssave.com or through our website, phmass.org. You can kind of get all the details on these. The good thing to know is they simply are requiring, you can see that HERS index, which is a form of energy performance. So it kind of ties into passive house being an energy performance standard. So I do want to thank Mass Save and acknowledge them for all the work they're doing to incentivize passive house projects. Massachusetts is now leading the Northeast region in passive house in large part because of these incentives. The last thing I want to mention with my time is that the state currently is redrafting its building code. Some of you may be familiar with this, others may be new to this, but it's happening right now. And the new building code is going to go into effect next year. There's lots of different parts to this, but the one thing I want to point out is the new code they're introducing. So we're going to have a base code and a stretch code. And then on top of that, we're going to have a specialized opt-in code. And that's what this slide is showing you. For large multifamily buildings in this new code, passive house will be required. And then for all other types of buildings, it will be one of the pathways that you can that you can qualify under. So this is coming down the line. It's open for public comment right now. You can go again to our website, phmass.org, and find out details about the code, how to comment, and all those sorts of things. But definitely something to keep in mind. We're seeing, the carrots with the incentives for passive house. Now we're starting to see the stick come through. So one way or another, we will all be doing passive house here soon. So thank you, and I look forward to today's presentation.
Thanks, Aaron. So now I'd like to turn it over to Mark Webster, who will be acting as the moderator for today's event. Mark?
Yes, thank you. And we have some great speakers coming up, so I'll try not to take too much time kicking us off. But my name is Mark Webster. I'm a structural engineer with Simpson, Gumpers, and Hager in Waltham. And I co-founded the SCI Sustainability Committee in 2005 and helped launch the SC 2050 commitment in 2020. So I'd just like to provide a little bit of context about what's happening in the structural world of late. The recent widespread realization that building construction itself emits large quantities of greenhouse gases has catapulted structural engineers into the heart of green building discussions. As I'm sure many of you have seen, over the next 10 to 15 years, when we must reduce carbon emissions by 50% or more to avoid the worst impacts of climate change, the embodied carbon associated with constructing new buildings will be greater than the emissions due to heating, cooling, and powering those buildings. And most of that embodied carbon is due to structure. So now that we have the attention of architects, building owners, and others in our industry, we have the opportunity to educate not only on embodied carbon, but also on other aspects of our practice that impact the environment, such as designing for material reuse and addressing thermal bridging, which takes us to Passive House, a highly energy efficient design approach, which is rising in popularity in the Boston area and across Massachusetts. Passive House design requires a tight building envelope free of thermal bridging hotspots. If we work on passive house projects, we need to understand these precepts to help make the projects a success. So I welcome you all to today's webinar and hope that it will expand your awareness of the many ways we can have a positive impact on our environment in the course of our practice. So to kick things off, I'll turn it over to Rob Haley.
Thanks, Mark, for that introduction. My name is Rob Haley. I am a mechanical engineer by diploma, but an architect wannabe, and I now know enough about structural engineering, more than I thought I would ever, after being involved with thermal bridging for the past 10 years or so. I'll start off with my presentation, which is right here. Can everybody see that? Okay, good. All right. Why is it not advancing? Here we go. Okay, so thermal bridging. Where does thermal bridging occur in a building envelope? Well, it can occur in the roof, where we have equipment screen posts or dunnage connections or parapet details that conduct heat out of the building. It can occur at balconies and canopies and sunshade connections where the structural elements penetrate the thermal envelope or pass directly through the exterior insulation. It can occur at cladding attachments, such as metal Z-girts or aluminum or carbon steel clips and rail systems. It also happens at relief angles and shelf angles for masonry veneer design. It can occur at rough openings at windows, and especially at lintels or flashing details that aren't paid attention to, or just simply the position of the window in the opening, where all these conductive materials talk to each other and pass the heat through the insulation. The foundation is also part of the building envelope. For example, wall to foundation transitions can be another source of thermal bridging. So those are some areas where thermal bridging can happen in a building. And the question is, why does it happen? Well, it's because the materials that we use in construction, mainly for commercial buildings, but also residential buildings, These materials are strong, but they're highly conductive, right? And that means that they have very low thermal resistances because they're highly conductive. And that's what's causing the problem. So why is it a big deal? Well, it's a big deal because the amount of heat that's being lost through walls and roofs is being underestimated. And we now know through demonstration, through three-dimensional heat flow modeling and hotbox testing, that the wall's R value can be reduced by as much as 50% just due to simple steel Z-girts, cladding attachments. So why is that important? Well, as the thermal resistances of our walls are going down, the amount of heat or the capability of our walls to transmit heat, the U value, is going up. And if we're not using accurate U values and R values in our energy code calculations like ResCheck or ComCheck, or when we talk about performance-based design like Passivhaus, if we're not using accurate R values, then we're just sort of turning a blind eye to what thermal bridging is actually doing to our wall assemblies. So how does that relate to Passivhaus? Well, in Passivhaus, and I'm not an expert by any means, but one of the critical requirements in Passivhaus is to reduce thermal bridging as much as possible, because there are requirements in Passivhaus for the allowable thermal conductivity at interface and transition details, okay? And much like the Model Energy Code 90.1 ASHRAE, by climate zone, there are R values and U values assigned that you're meant to meet for your wall assemblies. Now, those R values and U values, again, need to be the effective R values and U values, meaning they consider the effects of the thermal bridging. In either case, the main goal is to drive energy efficiency up and energy demand down, right? Which is why the energy code is getting stricter and stricter every time they release a new one. With Passivhaus, this involves a very, I wouldn't say rigid, but all parties need to work together to work on the design of the building, meaning the architect, the structural, the mechanical, all need to be on board on day one talking about these details, simply because, look, if you're the mechanical engineer, you need an accurate balance point temperature in order to design the plant for the building, to size it properly, to reduce cost, etc. And so everybody needs to play together and figure out, how are we going to obtain this goal of this low thermal conductivity at our interface details, which isn't always the case out there in the real world. So collaborative effort is important. One quick mention about continuous insulation, which is something that came out of ASHRAE, I think back in 2010. Is continuous insulation actually continuous if we have balcony and canopy connections poking through our exterior insulation? And the answer, of course, is no, because these connections create thermal bridges, which reduce the R value of our walls. And so saying we have R25, mineral wool in our exterior insulation cavity doesn't mean we have R25 as our effective R value. Okay, so we now know sort of where thermal bridging can happen in a building. We know why it happens, the conductivity of the materials. How do we quantify it? One way to quantify thermal bridging is to do three-dimensional heat flow modeling using transmittances, which is something that's been done in Europe for probably the past 20 years, even more, and has been happening up in Canada for several years now. And transmittance is just a fancy word for heat flow, right? And so if we take a look at a wall assembly, typically we can define the heat flows in three different formats, okay? Point transmittances, which are single points like a balcony or canopy connection. Linear transmittances, which are your parapets or your masonry relief angles that travel the perimeter of the building and are defined by length. And then your clear field transmittance, which is basically the wall itself without any other thermal bridging anomalies, okay? And when we model these heat flows correctly, we get a more effective and accurate heat flow value for our assembly. Let's take a look at how that's done. This is a very simple, straightforward, let's say canopy or balcony beam penetrating our wall assembly. Wall assembly is your typical steel stud. In this case, it's got some internal bat insulation, some exterior insulation, our dense glass, and our metal Z-girts. And the main point here is that that beam doesn't look like it's got huge surface area to it. Yet it is responsible for reducing the R value of this wall by almost 76% in conjunction with the steel Z-girts. You can see that if we look at the first column, we've got an exterior insulation of R15. With the interior bat, we're expecting to see R29 out of this wall. But what happens is, because of the steel Z-girts, it drops to R18.6. And then because of the steel beam, it drops further down to R6.9, call it R7. That's a significant decrease in R value that needs to be taken into consideration when we're doing our energy code math, okay? So what can we do about this beam to reduce the amount of heat that's coming out of the wall? Well, traditionally what is done is we use a thermal break. We make a break in that connection and we add either a material or a manufactured assembly, right, with a much lower thermal conductance than the steel in order to keep the heat in and keep the dew point out. This particular slide, yes, it's in metric units, but I like it because it's an important takeaway when you're thinking about using thermal breaks. And that is that the thermal conductivity of a material is a function of area, temperature difference, but also the conductance of the material, okay? And that is a function of thickness. And so all of these variables work together to sort of control the heat flow coming through that material. In this example, we've got two columns of two different materials. One has a thermal conductivity 4 times the other. That's noted by the red arrows. They have the same area, they have the same thickness, and it's the same temperature difference. But we can see down the bottom that the heat flow through the material with the higher conductivity is obviously higher than the one with the low conductivity. What happens if we change the thickness though? If we take half the thickness, what happens to the heat flow? The heat flow doubles, okay? So that's how those are related. What happens if we change the temperature difference to 10 instead of 20? The heat flow is reduced by half, right? That makes sense. So it's not rocket science, but it is some physics involved here with the first law of thermodynamics. And you just need to be cognizant when you're working with thermal breaks of, you know, what am I working with here for thermal conductivity? You know, and what is the heat flow actually going to be coming through this material? Am I making things worse or making things better, right? It's often overlooked, and I see so many details where these materials are very thin, and I think the concept is, oh, I've made a physical break, so I've reduced the heat coming out, but that's not always the case. So just be careful of that. And let's look at what happens when we do make a break in our beam. In this case, in the first column, I've given a range of R values just to see what the resultant R value of the wall would be, the effective R value. In most cases, the materials, the composite materials that are being used to break bolted steel connections, they have an R value of about 0.6, 0.7, something like that in that range. So here, if we look at the red arrow, I've got R 1.5. That's basically a 2-inch thick piece of material, right? And what has happened? Well, the wall has gone from 6.9 to 9.2. So we've reduced heat loss. We've increased R value by about 25%. But that took a 2-inch thick break. Now you'll also notice the steel Z-girts are still in the model. If we replace those with composite Z-girts or fiberglass Z-girts, that wall R value probably jumps up another 12 to 15 points, right? And so that goes back to addressing the clear field and the point transmittances in this model. What happens then if we use a material that's too thin? If we try and make a break that's too thin? Here again, if we look at the first column in the range of R values, even if we have a material that starts out with R3 and we only make it a 1/4 inch thick, its actual R value is 0.75. And if you now look at the resultant R value column, the next column over, what has happened to those values? They're actually lower than the beam alone passing through the wall. The beam alone passing through the wall, as you recall, was R6.9. Now we're at R6. So we've made the actual connection worse because we've increased the surface area of the connection without thinking about the conductance of the material, right? The thickness of the material. So it's just a point to make that when we start to try and improve these connections, we have to pay attention to the physical properties and the other design, criteria for these wall assemblies. In the chart below, you can see the blue line represents that steel beam at R7, and with a 1/4 inch break, the orange line, we've made things worse. Whereas with even a 1 inch break, we've improved things slightly. Okay. Thermal breaks are typically used to reduce heat loss in structural connections. True. But thermal breaks also serve a secondary purpose, which is to help keep the material surfaces within the wall assembly above the dew point. Here I've taken our beam model and I've taken a slice through the middle of it. I've assigned winter conditions in zone 5A, which is Chicago. And in the top image, you can see I've removed all the temperatures that are above the dew point from this model, okay? The black line here represents the exterior sheathing or the dense glass. And what we see is we might have a potential risk for condensation here in this particular building because we have temperatures that are below the dew point that are behind our exterior sheathing, okay? The image below is where we employ the thermal break in the beam area. And you can see that the temperatures have moved nicely outward into the insulation layer where they belong. And the only area now where we have some potential condensation risk is at the Z-girt connections, which we know can be fixed by using the composite Z-girts. So this is just to say that thermal breaks can function in 2 different ways. So lastly, the 3 main important takeaways from this, from my perspective, are when we're using thermal breaks to reduce heat loss and to improve energy efficiency and bring down energy demand, we just need to pay attention to structural integrity, compression, creep, thermal conductivity, obviously, because that's the whole point. And lastly, fire resistance, which isn't talked enough, in my opinion. The building code officials are going to start eventually looking at this hard because most thermal breaks that are on the market today are combustible technically. There are a few that are non-combustible, but how they may or may not affect the fire rating of the wall is important, right? So that's it for me. I tried to keep within my time limit. At this time, I'm pleased to introduce our next presenter, who is actually, I don't know if he knows this or not, he's the person who got me involved or interested in thermal bridging back in 2011. And that is Jim Deloisio, who's up next. Take it away, Jim.
Thank you, Rob. I know we had conversations 10+ years ago. I didn't realize I was a catalyst. Thank you for that. So I'm going to share my screen, I think, like that. Hopefully you can see my screen. Vibrant colors. We all good? So I'm going to riff off of some of the things, a lot of the things, really all the things that Rob talked about, especially collaboration. I like passive house design as a structural engineer because it really encourages the collaboration, which I think is really critical for a good project between architects, engineers, mechanical and structural, and all other kinds. That's what I like to do best as a structural engineer, collaborate with the rest of the design team. So you say passive house for a structural engineer, I say, well, thermal bridging. And then there's a little bit more involved with it too. So this is a different take, another practitioner's take on the thermal bridging issues. And I will keep to within my time as well. It's all about building performance, right? And what does that mean? We want low energy buildings. We want buildings that don't cause problems and don't cause discomfort. These are real world examples from things that I've seen. And what's funny is a lot of times they're caused by structural elements in the building envelope. You get condensation in the windows. It might not be the window. It might be the thermally unbroken lintel on above the window opening. You got ice dams and icicles. It might be that roof to wall connection intersection where the spandrel beam has some bad steel continuous thermal bridging things going on. It could be air gaps too. We could, it could be a combination, but I've learned firsthand minimizing problems in buildings that I see as a forensic engineer, as well as design engineer. These aren't my projects. I want to say that. These are my forensic investigation projects. When you see water leaking in a building or ceiling, you don't necessarily jump to the conclusion that it's a roof problem. When you've got horrendous, egregious thermal bridging at the spandrel conditions, and it's not just that they got to paint the ceiling every once in a while. On the upper right corner, there's some rusting of the steel, and this is a building that's only a year old. And the upper left, the lower right as well. Thermal bridging can cause structural problems. Hello, this is a big deal. These aren't passive house buildings. Not all of the building examples that I'm going to show you are passive house, but the principle applies to all buildings. I think it's time for structural engineers to wake up and realize we need to collaborate and minimize thermal bridging, whether it's passive house or not. Get yourself an infrared camera. They're cheap. They're 10 times as cheap as they were when I took these pictures 13 years ago, and Rob and I were commiserating over them. These aren't Rob's buildings either, by the way. These are shelf angles, or rather the warm brick adjacent to the shelf angles that represent continuous problematic thermal bridging. The mechanical engineer, the architect didn't anticipate tremendous heat loss that we see. So we took a little look, me and a committee with the sustainability committee. We looked at the unmitigated shelf angle detail with a steel angle continuous and going past the insulation that's ironically required for energy code and performance. But that represents the steel represents a huge thermal bridge with a U factor for this 3-foot tall area of 0.44, which is worse than a really bad window. You can do an alternative detail with an interior with a little fin plate every 24 or 32 inches on center or so, which reduces the U factor down to 0.13, which is like 70% reduction of the heat flow in that area. And it's not necessarily more expensive. AISC says it's a little less expensive because it's less steel. The big dumb shelf angle, time to get rid of it. It's got a 240% increase in thermal flow compared to the proper detail. Yes, structural engineers need to pay attention to what their details mean in terms of thermal flow. This is one kind of hand detailed option for that fin plate. It's basically a piece of a WT section, intermittent. Make the thermal bridging elements intermittent and you reduce a lot of the problem of thermal bridging. This is a concept. This whole thing that I'm presenting right now is basically conceptual as opposed to get out your calculators and use your computer programs. Get the concepts down right, and then the math will flow from that. The alternative is to use a proprietary system, which is very popular in Europe. This is a European so off-the-shelf design. Get it? With fins, proprietary manufactured fins. Again, minimizing the thermal bridging of the steel that goes through that insulation that's behind the brick. In Europe, they actually have a glass fiber reinforced plastic lintel, which I think is fabulous. You don't need flashing. You don't need to make it galvanized. You don't have any thermal bridging. It's just that in this country, we're reluctant to trust new systems. And so maybe someday we'll have the guts to use a system like that. This is what I did a few years ago to prevent thermal bridging at a hung lintel, with green being the fiberglass reinforced plastic angle, which you can get. It's $60 a linear foot. It's expensive stuff, but it basically is a thermal shim with the stainless steel bolts, because stainless steel conducts heat a third as well as carbon steel, as Rob pointed out. And this is the way it looked like in the field. It looked pretty good. But again, like Rob said, the thickness thickness matters when it comes to mitigating thermal bridging. The other thing for passive house and all kinds of buildings is it provides a good place to allow continuity of the air barrier, which also structural engineers need to think about as it impacts their structural details. This is another way to address thermal bridging at a shelf angle, and then I'll stop talking about shelf angles for a while. This is using polyurethane shims, thermally resistant shim elements, structural shim elements. You can get polyurethane in a variety of different strengths. You have to think about the fire resistance, but basically this is Tide and Krogstad's design methodology that my friend Mark Webster developed by way of coming up with a calculation to show the structural support of a shelf angle using thermal shims. Yes, you can have these elements in compression as long as you keep the compression load 10% of total to minimize of capacity to minimize creep, long-term creep. And then I click to the next one. Okay, Rob mentioned about clear field thermal bridging, which is steel. This is an example of an aspect of clear field thermal bridging. When you have insulation all the way outside the wall, but you have a parapet, if you don't insulate and wrap around completely around the parapet, you have thermal movement that goes through the top of the parapet. The heat doesn't give up, when it goes up, higher and higher on the parapet. You do need to seal all around it or use a thermal break assembly at the base. Infrared, again, get yourself an infrared camera. It really shows the thermal gradient. Purple is cold on a cold day standing inside. You really see the thermal losses. And that's why mechanical engineers beef up their mechanical systems, because they don't trust the envelope, and this is prone to condensation as well. If we need to minimize heat flow, we'll need to pay attention to this kind of thing. Again, another aspect of clear field. Cold form steel roof trusses. This is a roof overhang with a steel trusses, and I've never really understood how they can get away with this, quite frankly. They've got a really good system. It's a 100-panel system with a ventilated top to keep the roof cool and all, and good insulation above the roof deck. But then they forgot to even think about, the architect, the team forgot to even think about what happens with heat flow, in the soffit. What do you think happens? Well, the infrared camera doesn't lie. It lights up like a Christmas tree. It's horrific. My friend Russ Miller Johnson has a modification detail with a SIP panel modifying the edge. You got to do something creative if you're going to use highly thermally conductive cold form steel, roof elements in an overhang condition like this. Tricky stuff, interesting stuff, creative stuff, fun stuff to really solve, problems to solve. But you got to know it's a problem, because it's a problem. Okay, and then there's point thermal bridging, which isn't in terms of heat loss overall for the building, not such a big deal, but still in all, it provides an opportunity for Mr. Cole to come in and provide a condensation point, either inside the building, so you see, surface damage, or maybe even worse, inside the wall, where you don't see the problem until, there's been some deterioration of the studs. There's a lot of buildings that have conditions like this because they don't really reveal themselves as problems for until a few years after construction. So point thermal bridging is not unimportant. In terms of overall numbers, it's not a big deal most of the time, unless it's continuous. These are a couple of examples of low conductance thermal shim use and roof framing, where there's very low load on the structural elements. We've introduced the low conductance thermal shim, so the stresses are low. I've been known to be very bold when it comes to details that have very low loads. It's the big loads that you really got to pay careful attention to structurally. You also have to let your special inspector know that this is not a mistake. They didn't just put in a piece of packing styrofoam in the connection. These are stainless steel bolts and a designed compressive capacity of rigid insulation. And again, thickness matters. So the detail on the right, I probably wouldn't do today. And you can also use manufactured structural thermal break assemblies for steel-to-steel connections. There's a couple of different companies that have proprietary systems that you can design delegate into your projects. We do it all the time. You know, Syracuse University is one of our biggest clients, and they've come to require, you know, addressing thermal bridging explicitly for their design teams, even for their small projects. So anytime there's an overhang or a canopy or something, we use a thermal break assembly in the steel connection. And when we have the opportunity, we use really big ones. This is a really cool project in Verona Sherrill School District near Syracuse, New York. Yeah, moment connection. It was supposed to be just shear, but it was shear and moment. And installation worked really well. So it could be the biggest installation of a manufactured structural thermal break assembly in steel in the Northeast. I don't know of anyone that's bigger, but I'm not sure about that. And of course, for concrete balconies, when you extend the balcony out through the thermal envelope without any mitigation, the thermal envelope again will show a thermal gradient. This is a famous building in Chicago. It's beautiful, but they don't have thermal bridging at the faces. What do? You use a manufactured structural thermal break assembly. It's what you got to do. They're proprietary, but they're design delegated elements like the steel-to-steel elements. You used 100% of balconies and canopies in the European Union and Australia and even China, maybe 5 or 10% in this country. That's all. We just do it. It's kind of like Nike. We just do it. We just put them in. When you got concrete outside, concrete inside, you need continuity, you put in the thermal break assembly. Just do it. Integrating with architects for balconies and canopies, you can work with the architect to minimize the structural connection through the insulated envelope, which is eliminating, you know, the potential for thermal bridging altogether, so that the connection of the building is nothing more than shear, which is nice. You can minimize the connection, use stainless steel bolts. You can even use supports, vertical supports outside the envelope. So the outside elements are supported outside, the inside elements are supported inside. It's a collaboration thing. Quickly now, insulated headers. They come and go in terms of availability from manufacturers. You can build them yourself. There's no reason to use a solid wood header when you don't need it structurally. There's different options to develop both field applied and factory manufactured insulated headers. And finally, I was asked to talk about podium buildings because we see a lot of them going up now, where you have a steel or concrete platform where you build maybe a 5 or 6 story tall wood framed stud wall residential building. You have to separate the conditioned space from the unconditioned space below, and if you've got an unconditioned space below, like for parking. And so we've done this. We treat it kind of like a slab on grade. We just put insulation that's not super stiff, but stiff enough so it doesn't cause problems to insulate and isolate the interior finished heated space to the outside, the unconditioned space below. So that's my quick spiel, and I think I'm at my 15-minute mark here. So we'll talk about answer any questions after the presentation by the third presenter, who is going to be coming on board now, Paul Cunell from Ode Engineers. So with that, I say thanks for your time. Take it away, Paul.
All right. Hi, everyone. Hopefully you can see my screen. We're all good here. My name is Paul Cunell. I'm a project director at Ode Engineers. We're based out of North Providence, Rhode Island. We have offices in Boston as well. I am a structural engineer by trade, licensed in the state of Massachusetts, and I am educated as an architectural engineer. I really enjoy the integration with all of the members of our design team, and I try to carry that with me in my daily basis and how I approach different design decisions amongst all my projects. Today, my presentation is going to focus on the detailing and constructability review of thermally improved structural details. And I just want to highlight here, one of our projects under construction. This is the Loop at Mattapan Station. It is a multifamily project. at the Mattapan Station train station there, and it is going to be Passivhaus certified building. So some of the key topics, as Rob and Jim have touched upon, some of the key tenets of Passivhaus design are thermal control, air control, radiation control, and moisture control. Now, as part of my presentation, we're going to focus on thermal control, and specifically controlling of the structural system and the penetrations through the building envelope. And by controlling that thermal control, as you kind of saw in Jim's presentation, we hope to mitigate any issues with, moisture and frankly, the air vapor barrier as those penetrations go through the building envelope. Some of the key structural design considerations that we always have to take into account, but even more so in these connections, are the structural stability, the serviceability, sustainability, constructability, and the aesthetics of these different connections. And hopefully, if we can work with the design team and construction team on solving all of these issues, will result in a high performance building envelope. Now, I know as a structural engineer that's constantly kind of challenged with coming up with some of these connections, one of the biggest sort of hurdles in the design of connections is where to find information on how to design them. Quite frankly, today we're going to focus on steel connections. So if you open up AISC Steel Construction Manual, you're not going to really find a whole lot of information on how to approach these. And hopefully in the future, we'll be moving forward in that direction with specific design guides and things like that. But what I wanted to highlight here is some of the resources that we've curated over time and for the design of shelf angles, thermal bridging, and design of thermally broken or thermally efficient details. I want to point out a few of my speakers and moderators are in this list. And I encourage you to, with the slides that will be distributed at a later date, to really track down these these papers and presentations and explore them on your own. Particularly that last one with Jim and Mark is a great resource, and it's available to stream free online from the AISC organization. It actually goes through and details the Krogstad, Tide and Krogstad method, as Jim was mentioning, for economical design of shelf angles. We've all designed and detailed with these typical details. And it's time that we get away from these typical details, because you can see each one of these details, all of which I have drawn, and there's that continuous relieving angle that's penetrating the building envelope. That's that linear transmittance, those pictures that Jim was showing you, encouraging you to get your thermal camera and explore these. And what I want to express here is it really does not take that much effort to avoid detailing like this. And what we'll move on to next is I like to call like thermally improved details. These are not thermally broken details. These are knife plate connections or fin type connections, like Jim was mentioning, that move that relieving angle assembly or bent plate, depending on the distance from your spandrel beam, and it moves it outside the building envelope. Now, this accomplishes so many things for you that it's really, I can't stress enough how we should be going in this direction. One, you take that knife plate, put it at 2, 3, 4 feet on center, depending on what your design allows. That end assembly, the relieving angle assembly, is now, instead of needing to span a greater distance through the envelope and maybe potentially be a bent plate or even a stiffened bent plate, now you have a rolled angle assembly. It's cheaper, it's straighter. You can have the entire assembly on the outside of the building be galvanized, masked off at the inside, and all of your welded connection on the inside doesn't need to be touched up at the end. You just have a straight weld. As well as it's easy to provide the horizontal and vertical adjustability on the inside of the building through that dense glass as you're seeing there. Now, both of the previous speakers discussed collaboration amongst trades. And, you know, at times I like to play, like pretend I'm an architect and draw my details. So what you're seeing on the left is a detail I've drawn in a meeting discussing with the architect, the mechanical engineer, the building envelope consultant. And this is the early stages of the design, knowing we were going to be designing a passive house building, finally getting over the fact that, yes, you do need thermal brace. We do need to tackle the thermal efficiency of these details. It is not something that can be value engineered out down the line. This is a requirement, one of the key tenets of passive house design. And it's something we have a responsibility to address. But this detail on the left, this is where we started. This, putting some sizes to some of these members and some dimensions, allowed our building envelope consultant to take this, run some initial thermal modeling, and really influence what we ended up with on the right. That's our Revit Detail, and this is the detail that went out on our construction documents. So it really shows the need for that collaboration amongst trades. And I'm just gonna highlight on this detail here. So this is a 2-inch thermal break pad, sandwiched between 2 WTs with like basically an end plated, you know, 4-bolt end plate moment connection of sorts. The in and out adjustability is achieved through the slots on the long slots on the inside angle, and vertical adjustability on the outside angle that then that welded assembly gets welded after fit up. It's important to work with your building envelope consultant to address the location of that thermal break pad to ensure, you know, not only the thermal efficiency of the detail, but also like the constructability of the detail, where the position of the air vapor barrier is, the exterior sheathing, and so on. Now, we talk a lot about relieving angles, and I think relieving angles are an important thing to talk about, particularly in our masonry buildings. You know, we're being in the Northeast, we have a lot of masonry buildings, but some other areas of the building envelope, like our speakers have talked about, touched on, is, you know, dunnage platforms and roof screens. This is some example details in a recent photo of a lab building we've done here in the Boston area. Obviously, it's quite an extensive dunnage platform for a lab building, supporting all the mechanical units on the roof, and the associated screen to hide those units. But again, this is a thermal break pad sandwiched between cap and base plate, the height of which is coordinated with the architect in terms of the location of the roofing membrane and the insulation layer. But you can see that you can, as long as you can minimize or design the connection to minimize the compressive stress on the pad, these details are not that difficult to come up with. Other locations that you see these requiring thermally broken or thermally efficient details are at canopies, and specifically, you know, canopies that are penetrating the building envelope. You know, these could be locations where it's kind of coming through a curtain wall system, or just above a storefront at the interior of the building. And one of the things I want to highlight here is again, that collaboration piece is so important, because, you know, regardless of whether you're designing that connection yourself or you're delegating the responsibility to the connection designer, most of the time with these details, you're going to have like a bolted end plate moment connection. Now, most of the time, that most achievable by having that plate extended above and below that tube with the bolts extended out there as well. And what I want to highlight here is the position of that connection needs to be coordinated with the positioning of your curtain wall assembly or your storefront. Obviously, you know, when they come to install the storefront and they've got this big end plated splice connection to attach to, you know, you might run into some problems. So whether you're delegating that responsibility or not, it's important to make sure you're kind of giving the bounds of what needs to be achieved with other trades. You know, and I'm going to highlight here, the length of our presentation is not such I can walk through like a detail of the design here, but one of the things that I really want to highlight is to check out the thermal bridging and steel construction guide. Now, this guide is put out by the Steel Construction Institute out of the UK. And it's a really great resource on the design of these typical end-plated, bolted, thermally broken moment connections. Those two figures on the left are from that guide, and it really kind of walks you through the design of one of these connections, accounting for the shear and reductions through the pack layer of your thermal break, and the stress distribution from like your bottom flange and a bolted wide flange moment connection. So I really encourage you to seek out this resource and study it and check your connections, or use this as a guide for checking your connections. Now, the details that I'm presenting here, whether that's like a relieving angle or a canopy beam or whatnot, they've mostly been on an end plate with the thermal break pad in the middle. The other example is sort of like the prefabricated unit, which Jim showed in his very large thermal break detail. Very impressive there, but it's a prefabricated unit to transmit loads via direct tension and compression of the stainless steel fixings. And I think one of the things that's important to highlight of the difference between these, because I think it can get lost sometimes, is in this prefabricated unit, you know, that assembly that's kind of exploded on the right. When it's oriented like that, it's very similar to the end plate connection, but what you're doing there is you're getting like direct tension out of the top bolts. It's kind of like a double nut between your plates. And in the bottom connection, you have like a stainless steel sort of more or less like pipe that's in like direct bearing. Now, it's not to say that you couldn't use that bottom connection throughout your thermal break assembly, but in terms of these units, like I'm sure we've all kind of seen, it's important to recognize that that's what's being provided. So say in the condition where you maybe had uplift on a canopy, maybe you do need two of those bottom connections where you're trying to resist compression out of each side of that connection. So I want to end there, right on my 15 minutes, and open this up for further questions, or our next moderator.
Well, this has been great. Really appreciate seeing all those real life examples of how to address thermal bridging. We do have some time, which is great for questions. So I encourage you, if you have some questions for our speakers, put them into the Q&A chat. And we do have a couple here already that have not been answered. And I think one of them I could probably answer. About inducing bolt bending in these connections which go through thermal breaks, and it is in my opinion, you should account for that. And in the design methodology that we developed when we did some research on these connections, we do recommend including bolt bending when you have shear in the connection, in addition to the shear on the bolts. So that methodology is explained, I think, in one of the papers that Paul mentioned. There's a question about open windows. That sounds like that might be kind of a passive house design question, how that is dealt with. I don't know if anyone on the call could address that.
I'm happy to try. I'm not sure what the reference is. Is the reference to whether passive house can have open windows, or is it a function of the quality of the windows?
It seems to be a question about how you deal with heat transfer when you have operable windows, which users may want to open and close.
Oh, I see. Well, I mean, the passive house encourages the ability to open windows. We're not looking for a totally sealed envelope. We want to be able to allow air to flow into the building in a controlled way, such as through a passive house certified window. When the window's shut, there's no air leakage at all. When it's open, that's what the resident wants, and that's allowed, and it doesn't affect the overall balance of the heating and cooling system of the building.
Thank you, Hank. Hope that answers the question. We have a question from Mark about who is a good supplier for fiberglass products. Maybe that's related to, for instance, Jim's detail using the angle fiberglass or FRP angle in his brick shelf detail. It looks like he might be looking for a reference.
Yeah, used to have it right up there. There's a few manufacturers. I think Rob might be in a position to better answer this than from a manufacturer's point of view than us. I think Keystone might be one of the companies in Pennsylvania, but I defer.
Yeah, Liberty Pultrusions, they pull angles and hat shapes. I think they're in PA. So if you're looking for that shape, you're basically looking for pultruders, and then Liberty is one of them. That's the one I'm aware of anyway.
I will say there is a who puts it out? Is it ASTM? I can't remember, or maybe it's ASCE actually has a design standard for designing FRP plastic members. So if you do get into using those, I recommend you look that up. But I think it was a pre-standard, which has been published, and I believe that is being converted into an official standard. If it has not already been published, it will be soon. I think there's part of a question from Rashid, but maybe that was answered about a dead space under a wood parapet. Other than that, I don't see any other questions. So if Rashid could, if that question is not answered, if you could spell that out a little better. If not, I wonder if any of the speakers have any, since we have a few minutes, closing thoughts or other things maybe they wanted to squeeze into their presentations but did not.
I would love to add some closing thoughts.
Great.
You know, it was touched upon here. I mean, obviously this is a multifaceted problem, thermal bridging, but Jim's presentation really hit upon in a heavy way the building durability issues. I mean, the condensation problems that can result from these issues, never mind just the devaluing of the R value. These are of great importance. Durability is one of the key aspects of Passive House. We came to understand after the first round of Passive House design building in the early 70s that we were sealing up buildings, but we weren't taking into account these durability issues. And we ended up with a lot of buildings with sick building problems. And so Passive House has really built in durability, resiliency as a key factor, which is why when a project goes to FIAS or FEE for review, they're going to be looking for thermal bridges, not just from the point of view of what it's doing to an R value, but what the potential is for building durability issues. So, and then I would just reiterate what everybody's stated, and that is that it's critical that everybody come to a Passive House project with an understanding that it's not rocket science, as someone said, but it's different. And it has to be dealt with from the outset. The worst thing you can do to a passive house design is try to take a regular quote unquote design and then redo it as passive house at the end. That will produce a bad building and a lot of unhappy consultants in doing redraws. So it's critical that this upfront coordination happened. I like Paul's early sketches. He's showing sketches where you're talking about constructability and the nature of these details getting sorted out early on in the design team. It's really critical that this all happen early. So that would be my summary. Thank you very much. I think it was a great presentation.
Thank you, Hank, and the other organizers. I hope everyone enjoyed the presentation. I certainly did, and it sounds like slides will be forthcoming.
All right. Well, thanks everyone. And to everyone that called in, we hope to see you again at our next CMAS webinar. So take care and have a good day.